Hey there people, hope you're all good. I did a lecture on Friday. It didn't seem to go very well actually. I did feel like I conveyed what I was trying to convey properly to you. So I'm going to do a wee 20-minute video here or something, just to kind of go over again what I was going on about. Okay, and I've got around my wee shed here. I've got my wee camera set up. It's a little bit squint, but don't worry too much about that. So let's have a wee look. Right, I've got this kind of covered up. There's a bit of glare coming through, but I hope you can see it, and I'll check it out anyway. So right, now what I was on about with the vectors, I was wanting to kind of show you that whenever you get a motion, whenever you get a velocity in real life, it's generally made up of more than one component to that velocity. I'm going to give you an example of that. Say you have a wee plane or something, right? And it drops something. I suppose years ago you said it dropped a bomb, but nowadays we can say, well, it's dropping food aid or something like that. It's dropping an object anyway. And say this plane's going that way. When you drop this little item, it's going to fall like that, kind of thing. Right? And what you'll find, this velocity here, it's made up of two velocities. You have the velocity of the plane, or the force in that direction, and giving that a velocity. So when you drop that, that's still travelling at the same speed as the plane was travelling at. And say this plane's travelling at, I don't know, 100 meters per second, something like that. And then as it drops, what you'll find is you'll have a velocity caused by the acceleration of gravity there. So what we tend to call this is your V horizontal, your horizontal voltage, and then you'll call this your vertical velocity. Did I call that voltage? That's your vertical, sorry, your vertical velocity and your horizontal velocity. And with vectors, if you add them together, it will give you a resultant, which is the path that this takes. As you can see, it straightens out a bit at the bottom before it hits the ground. And that's because this vertical velocity, when you first drop it out of the plane, it's travelling at, it's very slow. It starts at 0 meters per second, but as it falls down a bit, it gets faster and faster. So you'll find the triangle down here would be more kind of like that sort of thing. So your resultant's much straighter, because this vertical velocity is getting faster and faster all the time, but you've still got your initial velocity there. Although that will slow down because of the winds pushing against it as it's going through the air. So that will slow that down. But what we do when you tend to evaluate these, you tend to not look at the friction at first. We'll just look at the general situation, and then we'll start applying friction. We'll just briefly look at friction, I would imagine. You'll maybe do it a bit more, getting a bit more depth when you're in your HNC and your HND. But so what we need to do then is we need to, if you have this, sorry, right, so so if you have this object falling and it has a kind of resultant velocity there, I'll put a wee r to show it's resultant. What we need to do is we need to find what its components are of that. What two velocities go up to make that velocity. And what we'll find is you have the horizontal velocity of the plane, and you have your vertical velocity pulling down by gravity. And that's pulling us down a way. And as I say, this does change. In real life, this will change. But as far as we're concerned, the questions that you'll look at and things, you'll just need to resolve one part of this. So let's see, we would say, well, what is the angle there? What angle would we be looking at? So we are going to be considering this angle here. And we would say that's where it's been dropped from. And it's falling like that. So we are concerned with this angle here. And say that was what? 30 degrees, this angle. We want to find what this one would be. What magnitude of this is. Let's say on here, and that's a horizontal velocity, and then we want to find this one as well, and this is the velocity due to the gravity at the point that we're looking at on this here. So that's what I was talking about the other day. So this would be like your adjacent, because that's close to the angle, and this is your opposite. And using so, ka, toa, and looking at this triangle here, we can say that the VH, or the horizontal velocity, is going to be equal to the resultant velocity times, remember the one that's closest to the adjacent, that would be the cos equals the adjacent divided by the hypotenuse. And this is, remember VR is the hypotenuse, and if I want to find out the adjacent, I just need to multiply this cos by the hypotenuse, and that's what I'm doing there. I'm multiplying, I'm transposing this equation, and if you imagine that this is your adjacent, this is the hypotenuse, and like obviously that's the cos of the angle. So your horizontal velocity is going to be equal to the resultant velocity times the cos of 30. I hope that makes sense. And the other one, this one here, the opposite, which is your vertical velocity, is, well, what is that? The opposite. And we've got the hypotenuse. The vertical velocity is the opposite, the resultant velocity is the hypotenuse. So again, what we're going to use, we're going to use cos. Sorry, I mean sine, because it's the opposite. The sine equals the opposite over the hypotenuse, so the opposite equals the sine of theta times the hypotenuse. I tend to put that there, actually. But, and that is, the opposite is going to be your vertical velocity, and that is going to equal the resultant velocity, which is h, your hypotenuse, times the sine of theta, or in this case it's 30 degrees. And you it's very handy to learn this. And as I say, this is what they call, see this here, that's 30 degrees, and that was the VR. You can write that as the resultant velocity, and that is at an angle of 30 degrees. And they call this the polar coordinate, or coordinates. And when you resolve it into your components, VV and VH, these are called rectangular components or coordinates. And that would be V R cos theta, and that's like your x coordinate in a graph. Can you see that? Oh, can you see that? Yeah. This, so what we've got is a polar coordinate, which just tells you how big it is and in what direction it's going. And these rectangular coordinates tell you, if you're drawing this in a graph, how far along it goes, but on its x axis, and then how high up it goes using this one on the y axis. So I'll show you what I mean with that. If you have coordinates, say you had a resultant vector of some sort, it could be a force, it could be a velocity, it could be anything. And say, what would that be, 3, 4, say this was 5 at an angle of 5. There's a wee magic right angle triangle, it's called the 3, 4, 5 triangle, Pythagoras, where if it's a right angle triangle and the opposite or adjacent is 3 and the opposite or adjacent is 4, the hypotenuse is always going to be 5, because so that's the hypotenuse, this is your opposite and this is your adjacent. If you look at Pythagoras and see that was 3 and that was 4, Pythagoras states that 8 squared equals O squared plus A squared, which is equal to 4 squared plus 3 squared, which is 16 and 9, it's 25. So 8 squared equals 25, so the hypotenuse equals 5. Oh, for God's sake, I can't see it. Right, so what I'm saying there, if you've got an adjacent that's 3, an opposite that's 4, and a right angle triangle, the hypotenuse is always 5 because of this. But anyway, and so you get 8 squared equals O squared plus A squared. That's 4 squared plus 3 squared equals 25. So 8 squared equals 25. If you get the square root, H, it's going to be 5. Yeah. Now, so the rectangular coordinates of that is basically what you would do when you look at a point on a graph. You would say then this is your X and this is your Y. So your rectangular would be 3, 4. It's just when you find a coordinate or a point on a graph, you say I go along 3 and up 4. And that is the point you get to. But in rectangular, we're saying, well, that's an actual length, as you went along 3 and up 4. It's as simple as that, basically. And if you want to change that to polar coordinates, you would have to say, well, the length of that is going to be 5, and you'd have to work out what the angle was going to be there. This angle here. Remember, SOHCAHTOA. SOHCAHTOA. If we are wanting to work out this angle here, what would we use? Give you a clue. See that? We've got the opposite and the adjacent, because we want to find this angle here. We know this length, we know what that bit is, because we've already done the Pythagoras for that. So what's this angle going to be? Well, if we've got the opposite and adjacent, if we look at SOHCAHTOA, what one's just got opposite and adjacent? The tan. So to find that angle, it's going to be the tan to the -1 over the opposite over the adjacent. Alright. And what that will work out is, so you get the tan to -1 of 4 over 3. You see that? A bit of light shining on that. That's tan to -1 of 4 over 3. And that will give you your angle for that. I hope this is making sense. And the reason I'm doing this is you really want to get this nailed in your head as soon as you can, because you will use, especially this, you'll use it constantly in all sorts of engineering applications. Forces, 3-phase electricity, single phase electricity, is endless. We will use this. You use it in looking at wing aerofoils, looking at rotating turbines. You'll look at, because in a rotating turbine you will have forces that are going in different directions that make up a circular kind of force. I know you can't see me when I'm doing this. I'm just going to do this, find out what this angle would be. Right, I don't know if you can see that there. That's far too bright. But anyway, if you get you find the function that says tan to the -1, and then it'll make a wee bracket. Then you put these values in, and that gives you the angle, and that comes out at 53.1 degrees. There. So I'll just try to clear that up, because I don't know if that came across very well the other day. Right. Right, when I was going on about gravity as well, about Isaac Newton, I was just trying to illustrate that there needs to be a force acting on a mass before anything kind of happens, before you get any dynamic behaviour. Next, I don't know about this year for NCs, but next year we'll do a thing called statics, and that's where you get forces acting where there's not any movement. It's stationary, it's still, but there is still forces acting on them. In that situation, these forces are always balanced, whereas in dynamic situations the forces aren't balanced, so you get some sort of motion because of it. And the one that we're most used to, I suppose, is gravity, and this was the first sort of indication of what was going on with this. I'll just briefly go over it again quickly. Right, gravity, that's, say, the mass of the Earth, and this is a wee object, the mass of a wee object falling towards the Earth. Right, and gravity works in kind of fields. See, well, what gravity is, it's the attraction of two masses to each other, and it's as simple as that, basically. And Isaac Newton worked out by experimentation and observation is this number here. It's called the gravitational constant. Right? No matter where you are in the universe, if you have a certain amount of mass and another mass, the attraction between them is kind of governed by this number here. It's a very, very, very small number. And to find the force on an object, the force on this object, you would work out the mass of the Earth plus the mass of the object, and then you would divide it by the square root of the distance between the two objects. So this distance here would be r, and obviously that's the mass of the Earth and that's the mass of the object. Now we all say that the force of gravity is kind of constant around the Earth. This is a value of 9.81 meters per second squared. This is like it's like an acceleration. So you accelerate at the same rate when you're falling towards Earth, but that is actually, that only occurs really at this where we are, where we float about on the surface. But it can change depending on, it basically depends on how far you are away from the centre of the Earth, determines the rate of acceleration. And obviously, see, the force of gravity is going to be much less when you're way out in space. Because, sorry, if you're way out in space, the attraction, or the attraction, or the force of the gravity pulling you towards that is going to be much less. And we just get this figure here and use that because that's what really occurs round about the surface. And you think, there's 20,000 miles round, well, circumference. So you can imagine if our atmosphere is only a couple of miles high that we generally use, it's not going to change very much. This figure 9.81 doesn't change very much. So basically, I'm just trying to say that the force due to gravity is worked out by looking at the two masses involved, combining them, and looking at the distance between them. And this figure here was worked out by experimentation and working out what this wee ratio is. And then I went on to say, like, it's a kind of misconception when we on the Earth we say, like, or when we weigh ourselves, we say we weigh 100 kilos or something like that. But that's actually our mass that we're looking at. If you have 100 kilograms, and that's your mass, the force due to gravity, or the force that occurs, or the force acting on that 100 kilograms, is going to be the mass times the force of gravity. And the force of gravity is at 9.81. That's in meters per second squared. Don't worry too much about the units just now. Just accept that's where they are. And that would mean the mass would be 100. So the force is 100 kilograms times 9.81, which is going to be 981 newtons. That is. And when you look at forces, it's always measured in newtons. And that is what you weigh, basically. That's your weight. So when you go into space and there's no gravitational force acting on you. So force equals mass times gravity, but when you're out of space, the gravity, you're too far away from any masses. Like what I was saying earlier, you're too far away from any masses to get any force of attraction from it. So that's why when you're out of the Earth's gravitational field in a spaceship, you don't have this. This is actually a value of 0. So you don't have any forces acting on you. Well, sorry, this will be 0. And you still weigh, obviously. You still have a mass of 100 kilos, but there's just no forces acting on it. There's not any gravitational forces acting on it. So that's why when you're in space, your weight equals 0. So when people say they weigh themselves on the Earth, they're actually just measuring the amount of mass they've got, rather than weight. Okay. I hope that made sense. What I'm going to do is quickly go over that graph I went over with the velocity time graph. I'm talking there about distance travelled and displacement, and what is the difference between that. Okay. Velocity time graph. Oops, I'll do it more like this actually. Right, so it's velocity. Can you see that? Oops. Velocity time graph. Come on. And this is time. Then we'll do V gradients. Graticules. Right, let's say 5, 10, 15, 20, 25, 30. And here you'll notice that this is minus 10, minus 20, minus 30, minus 40, minus 50 in that direction. So what I'm saying here is, see, if you're in a wee car and you're going in that direction, we're going to say that's positive. And if you're going in that direction, we're going to say that's negative. And the velocity is equal to the distance travelled divided by the time it took you to get there. So if you travelled 1,000 meters in 20 seconds, you'd be travelling at 50 meters in 1 second. You could maybe do it in miles per hour or what have you, kilometers per hour. But basically the velocity is the distance over time, or displacement over time. I tend to write this as that V equals S over T. This is displacement. Now what I'm going to do here is try and illustrate the difference between the distance travelled and your displacement. We're not going to add to it, we're going to, but also when you have a velocity time graph, as I was saying, imagine we're going at 30 miles an hour and you've done that for 20 seconds. If you've done 30 miles an hour, so sorry 30 meters per second, right, and you've done that for 20 seconds, so you've done 30 meters every second. Now you're going to do 30 meters for every second and you're going to do it for 20 seconds. So the distance you've travelled is going to be 30 meters per second times 20 seconds. And that's your velocity, and that's the time. So that's going to be what? 30 times 20 is 600 meters. Right? So you're going at 30 meters per second for 20 seconds. And what I was saying to you the other day was, if you notice something about that 20 times 30 is the area under here, in there. That's 600 meters. So if we do a velocity time graph and we get the area, we find the area under the curve, under the graph, that means we can work out how far it's went. We can work out its distance travelled, and we can work out its displacement. And remember, if you, so what we're saying, say the guy starts, or the person, a man or a woman, so he started at 0 miles an hour. He wants to go, say accelerates up to 10 miles an hour, or say 20. Right. So the velocity would be kind of, if you're accelerating at the same rate, your foot's in the pedal at the same bit, and you'll get up to 20 meters per second in 10 seconds. And then it travels for another 10 seconds at a constant velocity of 20 meters per second. Can you see that? And then again, so it accelerates in 5 seconds this time up to even 50 meters per second. He got a wee rush of blood to the head, and he's put the foot down and went, oops. He's went whoop, up to there. And that, what did I say? That was in 5 seconds, right? So we're at this point here. And this one here is at 20 seconds. And this one here was at 5 seconds. Was that 10 seconds? Let's say that was 10. And then he travels again, this is 25, he travels up to 35 seconds at a constant velocity of 50 meters per second. And then he decides, and this is up to 35, he gets to 45, he's going to stop and have a wee sandwich or something. So he stops at a wee lay-by, and he's decelerated in 10 seconds there. So if you imagine, so that's supposed to be at 35 seconds. So in 35 seconds he's going at 50 meters per second, and then he decelerates down to 0 miles an hour after 10 seconds. Right? Has his sandwich and his wee coffee, and he starts saying, I'm going to head back, and say he goes to 30 meters per second going home the way. Just he accelerates from 0 to 30 meters per second, right? And then he travels at constant velocity at 10 for another 20 seconds. And then what happens? Okay, what happens? He realises he's hardly got any petrol left. He actually runs out of petrol. And that, what did I say, that was 5 seconds, so that's to there. And then 4, 5, and so he just decelerates quite quick. It takes him 5 seconds to get to 0 miles per hour. So this is 30 meters per second, that's 30 meters per second, and that's 0 meters per second. And we went up to here, this is 20, this is 50, and he's went down to 0 there, and accelerated up to 30. So he's accelerated up to 20, went at constant velocity, accelerated up to 50, constant velocity, decelerated down to 0. He's went up to 30 meters per second, he's drove for a wee while, 20 seconds, and then he's run out of petrol and he's decelerated to there. What we want to figure out is how far has he got to walk home to get back to his house. So if we add this up, a half the base times the height, because if we split this into it's sort of it's blocks. See, we've got a triangle there, we've got a square there, and he's accelerated up in 5 seconds. So what we've got is a kind of triangle here. See that? And then he does that for 10 seconds and he decelerates over 20 seconds here. So this is going to be like that. That should be a bit flatter, I suppose. A bit more like that. You see that? And what we probably do is make that like that. So we've got a triangle there, a wee triangle there, a rectangle there, a rectangle there, a triangle there. And this one here, he accelerates up in 5 seconds, but he decelerates in 5 seconds. So we've got one triangle there, and a square there. So half the base, remember a triangle is half the base times the height. So half the base is 5 times 20, that's going to be 100 meters travelled. This is here is 10 times 20, so that's 200 meters travelled. This one here is 15 times 20, so that's 300 meters. This bit here was 5 there, and it goes from 20 to 50, so that's a half the base, which would be 2.5 times 50, which is 125. Hope you're following that. And then this bit here, that was 10 seconds, and that was 30, so that's 300 meters. Remember all these are meters. This one here is 10, 50, 5 times 50, because that's 10. A half the base is going to be 5, and that's all the way down there this time, so that's 50 times 5, it's 250 meters. So the total there, you just add all these up, so the total distance travelled in that direction is 100, 300, 600, 900, 1150, 1250, 1275, 1,275 meters in that direction. And then coming back, he turned round and he went from, in 5 seconds, he goes to 30 meters per second. So that's 30, so that's 30, and that's 5. But we do, again, it's a half the base times the height because it's a triangle. It's going to be, a half the base is 2.5 times 30, which is 60, 75. And this one's another 20 seconds at 30. What's 20 times 30? That's 600. And then another is going again from 30 to 0 in 5 seconds. So it's the same as that, 75. So that's 700. So the total is going to be in this direction. Remember, underneath the curve, underneath that axis, he's coming back the way. So that's going to be 600, 750 meters. So, what is his total distance travelled? Right? We'll be able to get in this now. So, total distance travelled equals 1275 plus 750 meters. $3,025 meters, and that's his total distance travelled. But what is his displacement? His displacement is this distance from here to where he is now. So in other words, he travelled 1,275 meters in that direction. So we have to take away the distance he's travelled back to the house. In other words, how far has he got to walk? And that's his displacement. So that's going to be the total distance. Well, so it's going to be 1275. Wait, when I got that wrong, that should be 2000. Sorry, that should be 2025. Yeah. I don't know where I got 3 from. And minus 750. And that's a 2. And that will give us 250 plus 275, that's 525 meters. So his displacement is 525 meters. In other words, that's how far he's going to have to walk home. Because he went 1275 meters that way, and then underneath here, he done 750 meters in that direction. Okay, I hope you're kind of getting that. And there was that other thing I'll just quickly go over that other wee thing about you throwing the ball. If you're a wee gadget person and you throw a ball up in the air, well, really you'd want to be, just try to, but you'd want to throw it up straight and then it'll come back down again, you're going to catch it. How does that look on a velocity time graph? Right. When you throw this, say you throw that at 20 meters per second, and that's when you throw the ball up, and this is your velocity here, and that's your time. This velocity, say your 20 is up there, meters per second. That's going to, when you throw it, it's going to instantly start at that speed, and then it's going to, so it's going to start at 20 meters per second, and it's going to slow down, slow down, slow down, slow down, slow down, till it actually gets to the highest point it's going to be, and at that point it's going to be 0 meters per second. It's going to stop moving, basically. So the graph like that would say that's just like it decelerating. So it starts off at 20 and it decelerates to 0. And that's at the top of its flight. And this is there, this point here, the top of the flight. And then what happens is it starts at 0 and then it starts accelerating and getting faster, coming back towards you. But what do we say about that? If it's going up the way, say if it's, what we'll say if it's going up the way, it's positive. Right? And if it's going back down the way, it's negative. It's basically just going in the opposite direction. So to be your standing relative to you, so you're saying, well, if up the way is positive, when it starts coming back down the way, I'll just say that's negative because it's going in the opposite direction. So this will accelerate from 0. Let's see. Whoa! So this will accelerate from here to 20, and once it reaches 20 mile an hour, that's when it's going to land in your hand again. And this is again, this is us not taking into account air friction and stuff like that, which would affect it, but just for the purpose of doing this, we just neglect them just now. But you will do that in HNC and stuff. And what you would say then is, what is the distance travelled? And say this takes, like, just say for instance 5 seconds and 5 seconds, right? So half the base times the height, that's going to be 10, well 2.5 times 20, it's going to be 50 metres. So it's travelled up the way. So it's travelled 50 metres up this way, and then it's going to come back down, and if you do this again, it's going to be 20, exact same thing, 20, and it's a half the base times the height. Again, that's going to be 50 metres, like that. Now, so the distance, the total distance is travelled is that distance and that distance. So total distance, oops, equals 100 metres. So the total distance travelled is 100 metres, but what is the displacement? The displacement is going to equal 50 going up the way minus 50 going back the way, which equals 0. And that's your displacement. Now, I'm hoping that's kind of cleared that up what I was trying to go on about the other day. Right, hope that makes sense. And I'll send you out a kind of tutorial that goes with this. And actually, I don't think I'm going to do any more dynamics with you. Eileen, I think, is taking over now. And I'm going to shift to another module. We've been short staffed. One of the lecturers off ill, and somebody else was going to start the other day, and they ended up not starting, and it's left us a bit short-handed. So Eileen's doing this, and I'm having to move an electrical module to the Wednesday, and I have to do an extra module on Monday afternoon with HNDs. But hopefully everything will be settled in the next week or so, and there won't have to be too much juggling going on. Okay, right, cheers then, bye.